The problem statement for today is to utilize ML to predict mechanical seal failure in a dry gas seal system and implement appropriate countermeasures. Basically, a quick brief on the background. So, the mechanical seal and seal support systems are usually used in turbo machinery applications where mechanical seal seals the process fluid from atmospheric contamination and vice versa. These systems together, so the mechanical seal, the seal support system, and the turbo machinery, they form the backbone of many process industries like oil and gas, food processing, pharmaceuticals, refining, and many such industries which deal with fluid. So, as you can notice that a failure of the mechanical seal means a complete termination of the process, which not only leads to significant lead time implications for production, but also poses hazardous environmental impacts if not curtailed, because a seal failure would mean the process gas getting leaked to the atmosphere and contaminating it. So it is very imminent to identify the probable causes of failure and decide and implement those appropriate countermeasures. At present, this problem is being solved by monitoring flow and pressure, and alarms have been set at different set points of flow and pressure based on normal conditions and are curated in such a way that they warn or trip the process entirely based on the kind of alarm that has been triggered by the flow. So there is a window of opportunity here because with the present solution, the user is warned generally after the seal fails. So that leads to the user having a damaged seal face, and in some very rare cases, a contaminated process environment. So the proposed solution is to use ML to work in tandem with flow and pressure instruments to predict the seal failure and ensure that a warning is sent before it is too late. So let's just break down it into the 6 stages of CRISP DM process. So the business understanding is that the industries which operate using turbo machinery or even turbo machinery manufacturers are target users for this kind of operations. And since these equipments are at heart of production, they play a key role in these environments. So the present solution is reliant on flow and pressure, which indicates the problem but does not exactly reveal the problem. So the proposed solution of sensors and networks will closely monitor seal health and warn before its failure. So for this, we need plenty amount of data from industries, which offers a great starting point. And this data can be visualized to understand probable failure cases and represent them statistically to understand what exactly contributes to what type of failure. So we already have industries which have been operating on these traditional methodologies for quite a long time. So there is a lot of data. From a data preparation standpoint, this flow and pressure data has been recorded very consistently. So, which means that there is data already prepared and labeled. So that is not a very big issue. For modeling, the modeling algorithm can be selected based on the kind of data that we have. So the algorithm will be dependent on the features that we're selecting based on our initial exploratory analysis. And then the hyperparameters can be selected and tuned for better results. So to define success, there are probably two successes that any model has, the outcomes and the outputs. So a probable outcome could be a reduced downtime, a reduced cost of repairs and replacement for the seal and seal systems. Output could be the ability of the system to warn before the seal fails. In deployment stage, the model can be released for real world application. This can involve many steps like integration into the model, supporting the customers, conducting training for customers, and so on and so forth. So for solution, we have two probable solutions. One is creating an embedded sensor networks wherein the sensors are mounted within the seal assembly. These closely monitor the seal health, the gap between seal faces, the wear and tear has been closely monitored to eventually predict how fast is the seal wearing down and how much more time can it sustain at a given operation rate. The next is to use the existing architecture of flow and pressure instruments to have an idea of how the pressure is changing with the increasing wear in the seal health, and then eventually giving in a prediction. So for design considerations, we can see that both the models they require edge kind of model location because we need immediate prediction with zero latency. Then for learning methods, it has to be an online learning method because the environment is dynamically changing and we need to ensure a consistent performance. The prediction also has to be online because the data changes instantaneously in these systems, and with an instantaneously changing data, we need a prediction that is updated on the latest operating conditions. So there are a few potential risks that are associated. So with model one, the most significant risk is the sensors. So these sensors that are being proposed are already existent in the market, but they need to be downsized to fit into the seal assembly. So we need to ensure that these systems do not hinder the seal's normal operation, nor do they affect the flow or pressure internally, which affect the process fluid. So since this model has to be trained on seal data is very confidential and very unique to every seal manufacturer, which means that this data is very difficult to get by. So that poses a huge challenge. Also, which means that this solution is customizable to a manufacturer and not a universal plugin for anyone. For Model 2, this uses flow pressure data from the existing architecture of transmitters. So there is already a lot of data available for training, and it does not need any additional hardware for operation, which makes it a more viable solution. The only solution is that in normal operation, there are some cases where the values surge instantaneously and these values go extremely close to the failure values. So this could be confusing for the model to differentiate. So based on these preliminary observations, it seems that model 2 is more viable to model 1. But with appropriate resources, we can